Video, we are going to talk about the area between two curves. So that's what we're going to find. The area bounded by these two curves, the red one, f of x is 4x minus x squared, the blue one, 4 minus x squared, and the y-axis. That and the y-axis, it seems so trivial, but you got to make sure you read that carefully. It is really important to know all the bounds of the area you're trying to find. So it was the red curve, the blue curve, and the y-axis. So that's why this white area on screen is what we're looking for. Had it said the red curve, the blue curve, and the x-axis, that would have been a little bit trickier because that could have been this area, or it could have been this area. So that would have been a little bit more confusing. So just make sure you are reading those carefully. Okay. One quick note before we get into the calculus here is it is important that you remember your algebra. You are expected to know what 4x minus x squared looks like. You're supposed to be able to recognize that that can be factored into 4x times 2 times 1 minus x. Which would have, 1 minus x. I factored that totally wrong. I'm sorry about that. It factors into x. You can only pull out an x, not a 4x. X times 4 minus x, which has zeros at, if you split and solve that, x equals 0 and x equals 4. So that's why the red graph has x-intercepts at 0 and 4. You're supposed to recognize this is a parabola. It has zeros at 0 and 4 and graph it from there. Similarly, you're supposed to be able to recognize this is a downward-facing parabola with a y-intercept of 4, and since there's no bx, you know that that's going to be the vertex also. You can also factor that to figure out 2 plus x. 2 minus x would have zeros at 2, and then back at negative 2, which isn't on my screen. I'm just making sure you remember that these are things you're expected to know how to do. Okay, moving on from that. Let's talk about the area now. Get back to the calculus. So I'm going to introduce this idea to you. Similar to things we've spoken about before. If I want to find the area of that entire white section, what I might start with is the area of just one piece of it. So just that pink little bit. This is a small amount of the area of the entire shaded region. So I'm going to call it the area of a strip, because it's like a little rectangular strip. If you imagine like taking that white space and like just cutting it into really thin pieces of paper, one of them would look like that. So let's talk about the area of that strip. And this is something I call dimensional analysis. Another one of those terms that I kind of made up. But what it means is we're going to look at it one dimension at a time. We're trying to find area, which is a two-dimensional space. But we can get there looking one dimension at a time. So let's look at this rectangle that we have here. That's the rectangle. I just literally just pulled it from there. It's the same thing. So if I want to talk about the area of that rectangle, I need to talk about the two dimensions of that rectangle. The first one, the length of that rectangle, would be the same as that distance, which is the distance between g of x and f of x. Or you could say it's g of x minus f of x. Which it certainly helps to actually do the subtraction. That is the same thing as 4 minus x squared minus 4x minus x squared. Please be careful about those parentheses because that will cancel out the negative x squareds. So we've got 4 minus 4x. 4 minus 4x is my length. What about the width? The width is a little bit trickier, or at least maybe less obvious. But we have a name for this width also, because what we're talking about is an infinite number of infinitely small strips. Now, sure, this isn't infinitely small the way I drew it, but if you can imagine drawing it smaller and smaller, and if I keep going, we have a name for the width of those rectangles. We call them dx, the infinitely small change on the x-axis. which means that the overall area of that pink space would be the area of any rectangle is the length times the width. So 4 minus 4x times dx. That is the area of this pink rectangle. Of course, the white area that we're trying to find is not just that pink area. It is made up of a lot of those little rectangles, an infinite number of those rectangles. But every single one of those rectangles is going to be the same thing. G of x minus f of x is going to make up the height, or the width of the rectangle, the length of the rectangle, and tiny little dx is going to make up the width of the rectangle. And that's going to be true for every single rectangle. What's important here is that g of x minus f of x is going to be a different value over and over and over again, depending on what x value we're looking at the time. So when x is, I don't know, a third, the f of x minus g of x is going to be this distance. When x is 2/3, f of x minus g of x is going to be a different distance in there. It's going to be variable. And that's why we need to do what we've done before when we want to find the sum of a whole lot of changing products. Because I didn't point this out before, but a reminder that this area, this dA that we have, the area of a strip, is a product. It's a y value, or really difference of y values, times an x distance. Well, we've already spoken about what to do if you want to add up a bunch of products of y values times x distances. This shouldn't come as a great surprise. We're going to integrate. So if dA is equal to 4 minus 4x times dx, then all of the dA's put together is going to equal the definite integral from start to finish. In this case, that's from 0 to 1, of 4 minus 4x dx. So our overall area is the integral from 0 to 1 of 4 minus 4x in respect to x. Well, that would be the antiderivative of 4 minus 4x, evaluated from 0 to 1. We can evaluate that. 4 times 1 minus 2 minus, well, if I plug zeros in there, it'll just be a bunch of 0. So that's 4 minus 2 is 2. 2 square units is our area. The key here is that we started with dimensions of the small little area, the dA, area of a strip. Using that language is important. The dimensions of that area, of that little strip, was 4 minus 4x by dx. And so the area of that little strip was 4 minus 4x times dx. And so the area of all of the strips put together is the definite integral of 4 minus 4x dx from 0 to 1. Now you might be asking, how would I know about the 1? And I'll point out two things. Number one, well, you can tell on the graph that the rightmost spot on our graph was when x equals 1. If you're ever not sure, if it's not obvious just by looking at the graph, or you don't have a graph, what you can do to find out is to say, well, that region is going to end. The region where the region bounded by 4x minus x squared and 4 minus x squared is going to end when the two graphs hit each other, which means when 4x minus x squared equals 4 minus x squared. And so we would just solve that equation. The minus x squareds cancel, so x equals 1. Would be, if we didn't already have the graph, how we could figure out what the limits of notation are, limits of integration are. Okay, pause and make sure you understand what happened in all of this, and then we're going to try another one, which is going to be slightly different, but really the same idea. In this one, we're going to find the area of the region bounded by x equals 3 minus 2y minus plus 2y minus y squared, which you might not know this, but that is a parabola. You can tell because one of the variables is second degree, the other is only first degree. And the other one is x plus y minus 1, which you should know by looking that is linear. I have those graphs shown on here. The area bounded by the two of them is the only area that's completely surrounded by those two, which is this area in here. That word bounded is important because on this side, because these graphs keep going forever, they won't be bounded. This area here would never be closed off. That's why we're not worried about that. We're only worried about the white area here. Now, you might notice that if I were to try and draw a vertical strip here, I can draw it just fine, but the height of that is a little bit confusing because both the top and the bottom are coming from the same equation. So that's a little bit tricky. We don't really want to have to do that. So what we're going to do instead is flip it on its side. Instead of talking about vertical strips, we're going to talk about horizontal strips. So we're going to break this region into an infinite number of small horizontal strips. They're all rectangles, so we can still find their area pretty easily. And then we're going to have to multiply that. I'll get to that in just a second. So to find their area, remember we're talking about the area of a strip. So we need the rectangle, so we need the length and the width. And this again is what I call that dimensional analysis, where we go one dimension at a time and then put them together to make the area. So the length of that from here to here, it doesn't matter which one you call the length, which one you call the width. I'll call that one the length, is the distance between the blue curve and the red curve. Now, the problem is that distance is a difference of x values, not of y values, because it's horizontal, not vertical. This is great. I already have my x value. X is going to be equal to 3 plus 2y minus y squared. This other one, if I want to talk about this x value here and subtract it from this x value here, I need to have this one, which comes from this equation, I need to have that written in terms of x. So that's what I'm going to do, which is not hard. I'm just going to write this as x equals -1 minus y. And so now my distance, the pink distance, the length of that rectangle is the higher x value, 3 plus 2y minus y squared, minus the lower x value, which is -1 minus y. Sorry, I'm trying to make it a little bit more legible for you. And I can do the subtraction there. It is -y squared. The 2y minus -y will make 3y. And the 3 minus -1 will make 4. So -y squared plus 3y plus 4. And the width is going in the other direction here. The width of this rectangle is that. I need a name for that. Well, I can't call it dx because it's not a change in x values. But it is a change in y values. The small infinite change in y values is dy. So I can say that the area of that little strip here is the length times the width, which means that the entire area is the definite integral of the little area. Let me actually clearly label this. When I said the area before, I'm talking about the infinitely small dA, the area of the strip. dA is the area of that whole thing. So the overall integral, or the overall area, is the integral of -y squared plus 3y plus 4 in respect to y, which means I need my limits of integration. I need numbers there. And this is where you need to think carefully. Because my integral is a product of a y, this is actually now an x value, times a y distance. When we say in respect to y, just like we saw with u substitution last week, the values up here need to be in values of y. And so this is the important part. You've got to be careful here. The upper and lower limits of integration need to be the y values where we start and where we finish. So on this graph, you can see that those y values are negative 1 and 4. If you didn't see it, if you didn't have the graph in front of you, or if it wasn't clear what the numbers were, you could get that by solving. When does our 3 plus 2y minus y squared equal our negative 1 minus y? When are those two things equal to each other? And so that would be y squared minus 3y minus 4 equals 0. And so we can factor this one. I'm doing this very fast because I expect you to be able to do it on your own. You can certainly pause and catch up if you need to. So our two solutions here are y equals 4 and y equals negative 1. That it would be an algebraic way of figuring out those limits of integration. If you would like, you can stop now and just integrate this on your own. Everybody should be able to. If you want to watch me do it, I will go through it right now. So the integral from negative 1 to 4 of negative y squared plus 3y plus 4 would be equal to the antiderivative integrated from negative 1 to 4. And this is going to get a little bit ugly, sorry. 4 cubed over 3 plus 3 times 4 squared over 2 plus 4 times 4 minus, and it's not a 0 here, so I actually have to do the math, negative 1 cubed over 3. In this case, the negative 1 is going to be squared, so it doesn't matter. And by the way, I could convert everything to be a common denominator, but you'll find in this case it's not really necessary. 64 thirds minus negative 1 thirds is 65 thirds. 48 over 2, well, I might as well just make that a 24 plus 16 is 40 plus 4 is 44. And then the 3 halves is by itself. You can certainly convert those all into thirds if you want. So that's 65 plus 132. Sorry, converting them into thirds will not be enough. You have to convert them into sixths if you really want to put them all together, which I wouldn't say is necessary in this case, but I'll do it anyway. 130 coming from the 65 over 3 is going to be 130 over 6. Plus 264, which is 44 times 6, minus 9, all over 6, which is 121, and 264 is 385 over 6, which I don't think reduces. And I could have made a mistake in there.